Now that we know a little bit about functions, we can start talking about properties that certain functions have. Just like we did with relations, we talked about different properties that relations can have. Well, here we're going to have different properties for functions. So some definitions. If we have a function f from a to b, we say that this function is injective, or we sometimes use the term one-to-one, if for every x and y in A, x not equal to y implies that f of x is not equal to f of y. Okay, so what this is saying is that the injective property means the following. If I have two different elements of A, of the domain, meaning that they're not equal to each other, so they're two different elements, then the outputs are going to be different. So if I have two different inputs, I have to have different outputs. They cannot go to the same output. Anyways, if I have a function with this property, then we say that the function is injective. So some functions are injective, some are not injective. We'll try to see if we can determine whether a function is injective or not. So here's a more intuitive way of thinking about it. It's from the book. So an injective function means that for any two x and y's in the set A, right, so here we have x and y. Of course, this is just a small part of set A, really. It's just showing that for any two x and y in A, this happens, meaning they go to two different outputs and not this, meaning you don't have a case where x and y go to the same output, right, where these two inputs lead to the same output. If you have a case like this, then it's not an injective function. It's still a function, probably, but it's, well, assuming it satisfies the properties of functions, it's a function, but it's not an injective function. In order for it to be an injective function, you need to make sure that for every x and y, they go to different outputs. Now, the book uses the word any. The word any is not so clear. I would have liked every. The word every is clear. This has to be the case. This has to be true for every possible x and y. Meaning I can't just pick two particular values, x and y, to make this true. I need to make sure that this works for every possible choice of x and y in order for the function to be injective. Of course, it could still be a function if it's non-injective. All right, now, another definition. A function f from a to b is surjective. In other words, well, using another term, it's onto. It's also known as onto. This means if for every little b in B, whoops, this shouldn't be in this fancy font. It's just a plain B, set the codomain. So if for every B in the codomain, there is an A in the domain such that f of A is equal to B. Here is the intuition. Surjective means that for every B in the set B, for every little b, again, the book uses the word any, not so clear. I would have used the word every. For every little b in set B, this happens, meaning there is an arrow that leads to B. You cannot have B just by itself without any arrows leading to it. This is in order for the function to be surjective. Of course, if you have a situation like this where B is by itself, the function could still be it could still be a function. Sorry, it could still be a function, but it won't be a surjective function. In order for it to be a surjective function, you need to make sure that for every possible little b in the codomain, there is an arrow that leads to B. Meaning you need to make sure that every element of the codomain is actually an output of the function. And finally, last definition, a function f from a to b is bijective, which is also sometimes called a one-to-one correspondence, if the function is both injective and surjective. Right? So if you have a function that's injective and surjective at the same time, then we say that the function is bijective. So here are again the definitions, and now let's look at some examples. So here, this is from the book, a nice little diagram showing 4 different examples. So let's take a look here at this top right. Okay, this top right. So this function is not injective. Why is it not injective? Well, you see here that there are two there are two different inputs, namely A and C, that lead to a single output too. So it's still a function because every input leads to exactly one output. Right? So we see A, B, and C, each of them lead to exactly one output. But you see here that if you look at the outputs, there is an output here, this 2, that has 2 inputs going to it. So therefore, it fails the injective property, because the injective property says that for every x and y in A, if x is not equal to y, then f of x is not equal to f of y. And yet here we have 2 different elements of A. We have this little a and little c, but f of little a is equal to f of c because they both have an output of 2. So this function is not injective. However, this function is surjective. Why is it surjective? Surjective means that for every output, there is at least one thing going to it. Well, if we take a look at both of these outputs have arrows, at least one arrow leading to them. Right, so this one has an arrow leading to it. This one has actually 2 arrows leading to it, but it's still fine. Now, if we look here, let's see at the bottom left. Okay, bottom left. It's not surjective because here you have this 3 all by itself, nothing going to it, nothing leading to it. Okay, so it's not surjective. Well, this function here, the bottom right, let's go back here. Sorry, the bottom left. This bottom left function is injective. It is injective because every input leads to a different output, meaning you don't have 2 different inputs going to the same output. So it's therefore injective. Let's take a look at the bottom right now. So it's neither injective nor surjective. Why is it not injective? Why is it not injective? Well, you see here that A and C lead to the same output, so it's not injective. It's also not surjective because you have this 3 here by itself. Now, top left, this is both surjective and injective. It's injective, well, because each input leads to a different output. So there are no 2 inputs that go to the same output. And it is surjective. It is surjective because every output in B gets reached. We are able to reach every element of B. Now, because this function is injective and surjective, it is therefore bijective. Okay, so again, 4 different functions, and some of them have, they don't all have the same properties. Some of them have one property and not the other. Some of them have both properties. One of them has both properties. One of them has none of the properties. So 4 nice little examples. Now let's do some more examples. Let's consider the function f from the set of real numbers to the set of real numbers defined by f of x equals x squared. You've seen this before. Now, is f injective? Is f injective? Well, no. Because let's take a look, for example, 2 is not equal to -2, obviously, but f of 2 is equal to 4, which is also equal to f of -2. So what do you have here? You have 2 different inputs, right? 2 and -2 that both lead to the same output. So that violates the injective property, right? The injective property says if you have 2 different inputs, they cannot go to the same output, right? If x is not equal to y, then f of x cannot be equal to f of y. But here we see x and y, they're not the same. 2 is not equal to -2, and yet f of 2 is equal to f of -2. So f is not injective. Is f surjective? Is it surjective? In other words, is it possible to reach every element of the codomain? No. And there are many examples you can give here, but for example, -2 is in the codomain, but there is no little a in the domain such that f of little a is equal to -2, meaning there's no way to get x squared be -2. Right? There is no input, there is no possible input to f such that f of that input, meaning that input squared, would lead to -2. Right? Because you square any real number, you'll get either 0 or positive, but you won't get a negative result. So therefore, f is not surjective. Again, in plain English, what this is saying is there are some elements of the codomain that are impossible to reach. For example, -2 is in the codomain, but it's impossible to reach it. Is f bijective? Well, this is easy. No, since it is not injective, and also since it is not surjective. But one of those would be enough. So therefore, it's not bijective. Another example: same function, f of x equals x squared, but now we change the domain and the codomain. Instead of using r to r, now we're using n to n, the natural numbers to the natural numbers. So we're sort of restricting this function to only deal with natural numbers. So you give a natural number as input, and you get a natural number as output. So let's ask the same questions. Is f injective? Answer is yes, since if a and b are any two different natural numbers, f of a will not be equal to f of b. In other words, a squared will not be equal to b squared. And this didn't work in the previous example, because there we were dealing with negative numbers too. But here we're not dealing with negative numbers. We're only dealing with positive integers. So we don't have to worry about that. So this function is now injective. Again, it's a different function from before, but it's also called f. But this f is now injective. Is F surjective? So the answer is no. For example, and there are many counterexamples, but here's one. 2 is in the codomain. Right? 2 is a natural number. It's in the codomain. But there is no input to the function. There is no a in the domain such that f of a would be equal to 2. There is no input that you can give to the function. That, remember, it has to be a natural number. The domain is n. So what input could you give to the function such that that input squared would be 2, right? It would have to be square root of 2, but square root of 2 is not a natural number. So therefore, f is not surjective. Is f bijective? No, since it is not surjective. Okay, so we've seen examples of functions that are or aren't injective or surjective. Now let's get more formal about it. How do we prove formally that a function is or isn't injective? So let's remember the definition. A function f from a to b is injective if for every x and y in a, x not equal to y implies that f of x is not equal to f of y. So how to prove that a function f from a to b is injective? So there are actually two methods. The goal is to show that for every x and y in a, if x is not equal to y, x not equal to y implies that f of x is not equal to f of y. So there are two methods, as I said. The first one is direct method. And what we do here is we show that if x is not equal to y, then f of x is not equal to f of y. It's direct, right? We're just doing exactly what what we need to prove directly. This, right, x is not equal to y, then f of x is not equal to f of y. So if this, then that. So what does that look like? So it's a direct proof, right? So we start off by saying, suppose x and y are elements of a, and x is not equal to y, right? So in other words, we suppose that the if part is true. Then we do some steps in the middle, and then we end, therefore, f of x is not equal to f of y. So we prove that whenever x is not equal to y, f of x must therefore be not equal to f of y. So that's the direct method for proving that a function is injective. However, in practice, this direct method, as described here, is not easy to use. Much easier is the following: the contrapositive method. Now, usually contrapositive is more complicated than direct proof. And here, it is more complicated in a sense, but it's easier to use nevertheless. So how would the contrapositive method work? Well, what we're trying to prove is, at the very essence, what we're trying to prove is if x is not equal to y, then f of x is not equal to f of y. Well, what is the contrapositive of that? All right, so here's where, things that we learned a few weeks ago come back. What is the contrapositive of this conditional statement? Well, here it is. We want to show that if f of x is equal to f of y, then x is equal to y. Okay, so think about it. Make sure you understand why the contrapositive of this is this. Okay, so how do we prove this contrapositive? Well, straightforward. We suppose that x and y are elements of A, and f of x is equal to f of y. Then we do some steps, and then we end by saying, therefore, x is equal to y. So thereby, we are proving that if f of x is equal to f of y, then x is equal to y. Okay, now how to prove that a function is not injective? So this is easy. It's finding a counterexample, right? So what does it mean to say that a function is injective? It means that if x is not equal to y, then f of x is not equal to f of y. Well, to disprove that, you would find x and y in A such that x is indeed not equal to y, and yet f of x is equal to f of y, right? So in other words, disproving the injective property, or proving that that a function is not injective. How about surjective? Proving that a function is or isn't surjective. So recall that a function f from A to B is surjective if for every little b in B, again, I made a mistake. There's no reason for this to be in the fancy script. It's just a plain b, this b, just like this b right here. So a function f from A to B is surjective if for every little b in B, there is a little a in A such that f of A is equal to B. So how do we prove that a function from f from A to B is surjective? Well, we must prove that for every little b in B, there is a little a in A such that f of A is equal to B. Such a proof will have the following form. It will start by saying, suppose B is an arbitrary element. Suppose little b is an arbitrary element of the set B, meaning, so B is in the codomain. Then we'll do a bunch of steps, and we'll end off by saying, therefore, there exists a little a in A for which f of A is equal to B. Right, so we'll find an element in the domain for which we'll call that element little a, for which f of little a is equal to B. Now, whatever reasoning we use, we must take care that our reasoning works for every little b in B, meaning I cannot pick a specific b in the codomain. It has to be arbitrary, meaning our reasoning has to work for every possible choice of b in the codomain. Meaning I can't just say, okay, I'll pick 1 as my choice for b and show that it works for 1, because that's not enough. It just works for that number, but I need to show that it works for every possible element of the codomain. So we'll see examples of that. Now, how to prove that a function is not surjective? Well, surjective means that for every b in the codomain, there is an a in the domain such that f of a is equal to b. Well, the way to disprove that would be to find some little b in the codomain such that f of a is not equal to b for all a in the domain. Okay. By the way, this is what we did in the previous example. How did we show that f is not surjective? Well, we found an element of the codomain of B, right? This 2, so 2 is in the codomain, and we saw that there is no a in the domain such that f of a is equal to 2. So we have proved that the function is not surjective. All right, so more examples. How to prove a function is or isn't surjective or injective. So consider this function, the function f from r to r. Okay, again, this this should have been in the fancy script, but sorry. So suppose we have a function f from the real numbers to the real numbers defined by f of x is equal to 3x minus 5. Let's prove that f is injective. Now, how do you know that this function is injective? Well, meaning how do you know to even try to prove that it's injective? What gives you the intuition? Well, I would suggest trying a few examples, like try plugging in a few numbers into the function and seeing if it looks like it's injective, seeing if you can find a way to make two different inputs go to the same output, or whether you think it's impossible for that to happen. If you try a few examples, you'll get an intuition probably that it is injective. But now we want to formally prove it. We want to formally prove that f is injective. So we'll start out by saying, suppose x and y are elements of R, meaning they're elements of the domain, and f of x is equal to f of y. Remember, we're using the contrapositive approach, which as I mentioned, is easier to use here. So suppose, again, we have f of x is equal to f of y. Well, if f of x is equal to f of y, that means, well, what is f of x? F of x is 3x minus 5. What is f of y? Well, based on the definition of the function, it is going to be 3y minus 5. So if f of x is equal to f of y, that means 3x minus 5 is equal to 3y minus 5. Now I could add 5 to both sides. So I have 3x is equal to 3y. I could divide both sides by 3. So I'm left with x is equal to y. So what did we see here? We started by supposing that f of x is equal to f of y. And the conclusion was that x is equal to y. That proves that f is injective. Again, what we're proving is really the contrapositive of the injective property, which is equivalent to proving the injective property itself. Okay, let's prove that f is surjective. So consider an arbitrary element b in the codomain. Right, R is the codomain, so R is of course the domain as well. But here I'm pointing out that consider an arbitrary element in the codomain. We'll call this element B. We need to show that there is some element A in the domain such that f of A is equal to B. That is, we need some. I'm sorry, this is a mistake. Sorry, that is, we need some little a in the domain such that 3a minus 5 is equal to b. Right, so in other words, we need to find an a such that f of a is equal to b. Well, what is f of a? F of a is 3a minus 5. So we need to find an a such that 3a minus 5 is equal to b. Well, that's, very easy algebra equation. I'm not even going to show the work. You can do it very easily on your own. So solving for a, we obtain a is equal to b plus 5 divided by 3. Okay, great. Now, let's note the following. Given any b in the codomain, or whatever, in the set of real numbers, it will always be the case that b plus 5 divided by 3 is also a real number. So in other words, given any b in the codomain, this will be in the domain. This element will be in R, which is the domain. And further, note that if we do f of this thing that we found, of this a, right, f of b plus 5 divided by 3, well, let's follow the definition of the function. It's 3 times the input minus 5. So that's 3 times this fraction minus 5. Well, the 3's cancel each other out. So we're left with b plus 5 minus 5, which is equal to b. So what did we get here? We found an input to the function that leads to the output of b. But our reasoning was not specific to us to a certain value of b. It didn't just work, let's say, when 3 is equal to 17 or when 3 is equal to 73, sorry, where b is equal to 17 or b is equal to 73, this reasoning works for every possible value of b. So take any b in the codomain, this reasoning will work. Right? Take any b in the codomain, if you do f of b plus 5 divided by 3, you'll get b. Thus, given any b in the codomain, there is going to for sure be an a in the domain, specifically this a that we found here, b plus 5 divided by 3, such that f of a is equal to b. Sorry, you got a little cut off here, but this is the value that we found before. But the point is, again, given any b in the codomain, there is going to be an a in the domain, specifically this a, such that f of a is in fact equal to b, as we saw here. So what did we show? We showed that there is always possible to hit or to reach the elements of the codomain. No matter which element of the codomain you'll pick, it's possible for the function to reach it. So that is exactly saying that the function is surjective, meaning every element of the codomain gets reached by the function. Okay, great. Another example, consider this function f. So this is a little bit of a strange domain. So the domain is the set R minus the set just containing 0. So this here is a set, right? In other words, the result of the minus operation is a new set. This set contains all real numbers except for 0. So it contains like 1.5 and 0.5 and 2 and pi and 73 and all that. So it includes all real numbers except for 0. Okay, whatever reason, that's the domain. The codomain is R. I'm sorry, this again should have been the fancy R, the set of real numbers. And the function is defined by f of x equals 1 over x plus 1. Now, you could, by the way, you can see why we excluded 0 from the domain, right? If we would have 0, if we would allow 0 to be in the domain, then we would have a case where we have 1 divided by 0, which is not allowed. So to avoid that, we made sure that the domain did not include 0. So therefore, we never have 1 divided by 0. All right, let's prove some things about this function. So let's prove that f is injective. So suppose we have x and y in the domain, and f of x is equal to f of y. Well, then, based on the definition of the function, so what does it mean f of x? F of x is 1 over x plus 1. F of y is 1 over y plus 1. We know that f of x is equal to f of y, so these two things are equal. Well, we can subtract 1 from both sides, so we have 1 over x is equal to 1 over y. Now, if 1 over x is equal to 1 over y, it must be that x is equal to y. So what did we do? What we've done here is we said, by supposing that f of x is equal to f of y, we have shown that x must be equal to y. So we proved that this function is injective, right? More technically, what we've done is we proved the contrapositive of the injective property, but that's equivalent to proving the injective property itself. Now let's prove that f is not surjective, not surjective. Okay, and here's the proof. Consider 1, the element 1, that is, it's an element of R, meaning it's an element of the codomain. It's an element of the codomain. Now, let's say we would want to have f of a is equal to 1, meaning if you want to say that the function is surjective, it has to be possible to do f of a is equal to 1, right? In order for the function to be surjective, you have to be able to reach 1, which is in the codomain. So in order to have f of a is equal to 1, what would that mean? Well, what is f of a? F of a is 1 over a plus 1. So we need to have 1 over a plus 1 is equal to 1. But what that means, in order to have that, we need to have that 1 over a is equal to 0, right? If 1 over a plus 1 is equal to 1, that means 1 over a is equal to 0. But that's impossible. It's not possible to make 1 over a be equal to 0. So there is no way to do f of a is equal to 1. And yet 1 is an element of the codomain. But the point is, it's an unreachable element. There is no way for this function to reach 1 as the output. So the function is not surjective. Another example, and here's quite a tricky example. So consider the function g, and here's the domain of g. The domain of g is z cross z. So that looks pretty interesting. The domain of g is z cross z, and the codomain is also z cross z. So this is rather interesting. Normally, a function has a number as input, right? So like an element of z or an element of r. Here, the function has an ordered pair as the input. So it's an element of z cross z. That's the input. In addition, the output is not a single number, but rather it's a pair of integers. So it's an element of z cross z. So it's a function from z cross z to z cross z. And here is how it's defined. G of m comma n. Remember, the input is an ordered pair. Now, really, we should write G of with two pairs of parentheses, right? We should have another pair of parentheses inside here, but we don't write that because it looks weird. But really, the input of this function is an ordered pair, but we just write it as G of m comma n is equal to another ordered pair given by m plus n comma m plus 2n. All right, so now, before we prove anything about this function, let's do some quick examples of using this function, plugging in some inputs. So some examples. G of 5 comma 6. G of 5 comma 6. So following the definition, it's going to be 5 plus 6, so m plus n, comma 5 plus, so that's m plus 2 times n. So 5 plus 2 times 6. Simplified, that is 11 comma 17. So notice again, the output of the function is a pair of integers. Another example, G of 3 comma negative 3. That's 3 plus negative 3, comma 3 plus 2 times negative 3. And that comes out to be 0 comma negative 3. Another example, G of negative 3 comma 3. All right, so the opposite order, that comes out to be 0 comma 3. So notice the outputs are not the same. Right, even though the zeros match up, but since the negative 3 is not the same as 3, this ordered pair is not the same as this ordered pair. They're not equal. So these two outputs are not equal. Okay, now that was just some examples to give us a feel of what the function is doing. Now let's prove some things about the function. Now, I wouldn't ask you about such a function to determine whether it's injective or surjective, right? Just looking at this function or even doing some examples, it's hard to see whether it's injective or surjective. But here's the thing, I'm telling you right now, or I'm about to tell you whether it is injective or surjective or both or neither. All we'll need to do now is prove whatever properties it has. So we're going to now prove that G is injective. Again, I wouldn't expect you to figure out for this particular function that it's injective. Some functions, it's easier to figure it out that they're injective, but this one, it's fairly complicated. But all we need to do here is prove that it's injective. So same process, but here it's more complicated because each input to the function is not a single number, but rather a pair of numbers. So suppose we have two pairs of numbers. We have this pair, which is m comma n, and another pair, which is k comma p. And these both are two different elements of the domain, z cross z. And suppose that G of m comma n is equal to G of k comma p. That's the standard way of starting off a proof that a function is injective, right? We take two elements of the domain and we say, suppose that the output of those two elements is the same, right? That G of the first element is equal to G of the second element. Then, well, let's follow the definition of G. If G of m comma n, well, what is G of m comma n? That's m plus n, comma m plus 2n. Then G of k comma p is this. So since these are equal, we know that these are equal. Well, so going a step further, if these two pairs are equal, that means the corresponding items in the pairs are equal, meaning this m plus n must equal k plus p, and m plus 2n must equal to k plus 2p. Okay, so we have that m plus n is equal to k plus p, and m plus 2n is equal to k plus 2p. Thus, well, here's a nice little trick. We're going to do m plus 2n, which is this, minus this one, minus m plus n. Now, let's see what that's going to equal to. So m plus 2n by itself is equal to k plus 2p. Okay, so m plus 2n is equal to k plus 2p minus m plus n, and m plus n is just k plus p, so it's minus k plus p. So this equality is true. Again, this m plus 2n matches with k plus 2p. They're equal. And the minus m plus n matches with this minus k plus p. Now, why do we do this? Well, you'll see in a second. So simplifying a little bit, we get m plus 2n minus m minus n is equal to k plus 2p minus k minus p. And simplifying, so we see that we have an m and minus n, so those cancel each other out. We have a 2n and a minus n, so that becomes just n. So we have n, and then on this side we have k plus 2p. Sorry, we have k and minus k, they cancel each other out. We have 2p minus p, that just becomes p. So we end up with n is equal to p. Okay, great. Going a step further. Now, let's say we do this, m plus n. Well, we know m plus n is equal to k plus p. Okay, so m plus n is equal to k plus p minus n, but we know n is equal to p. So minus n is the same as minus p. So again, m plus n is equal to k plus p minus n is equal to minus p. So therefore, this equality is true. And if we simplify, we get that m is equal to k. So what do we have? Since we found that n is equal to p, and we also found that m is equal to k, it follows from that m comma n is equal to k comma p, right? M is equal to k, n is equal to p, right? The corresponding elements, the corresponding items in the pairs are equal, so therefore the pairs themselves are equal. That's the end of the proof that G is injective. What did we do? We said, suppose that G of m comma n is equal to G of k comma p. And the conclusion is that m comma n must equal to k comma p. So we proved the contrapositive of the injective property, and therefore we proved the injective property itself for function G. Next, let's prove that G is surjective. So consider an arbitrary element b comma c, the ordered pair b comma c, which is in the codomain. Sorry, we need to show that there is an element in the domain, which will look like x comma y, such that G of x comma y is equal to b comma c. That is, well, what is G of x comma y? Well, G of x comma y following the definition would be x plus y comma x plus 2y. So we need an x comma y such that x plus y comma x plus 2y is equal to b comma c. So we need to find x and y. That is, we need to solve the following system of equations for x and y. In other words, we know that x plus y is equal to b. And we also know that x plus 2y is equal to c. So we need to solve this system of equations for x and y. We're trying to find the ordered pair x comma y, so we need to solve first for x and y. And then we'll put it together in a pair. So to solve the equations, you can try different ways. You probably learned some techniques in pre-calculus or some other class. So I don't know what this technique is called, whatever, I'm just doing it. So we know that x plus y is equal to b. So that means that x is equal to b minus y, right? Subtracting y from both sides. Next, I'll say the following. I'll say we know that x plus 2y is equal to c, right? That's the given equation. So now what is x? X we saw here is b minus y. So that's b minus y plus 2y is equal to c. Well, here we have b minus y and plus 2y, so that becomes b plus y is equal to c. And we can solve for y, that gives us y is equal to c minus b. So we've solved for y. We still need to solve for x, right? Even though we have x is equal to b minus y, but we still have y here. we need to have x in terms of b and c, but not in terms of y. So let's go a little bit further. So we know that x is equal to b minus y, right? B minus y, but that's now we know that y is equal to c minus b. So that's x is equal to b minus c minus b. So x is equal to b minus c plus b. So x is equal to 2b minus c. So we've solved for y. So y is equal to c minus b. We've solved for x. X is equal to 2b minus c. We're not yet done the proof, so let's continue. Since we found that x is equal to 2b minus c and y is equal to c minus b, we will set x comma y to be 2b minus c comma c minus b. Right? Just the values that we solved, x comma y. Now note that given any ordered pair b comma c in the codomain, I'm sorry, there should be parentheses around this b and c. I'm just whatever. There should be parentheses here around the b comma c. So given any ordered pair b comma c in the codomain, it will always be the case that the ordered pair 2b minus c comma c minus b will be in the domain. Okay, so that's true because the b comma c are going b and c are integers. So therefore 2b minus c is an integer and c minus b is an integer. So this is true. Note further that g of this ordered pair, right? G of 2b minus c comma c minus b comes out to be what? Well, if you follow the rule of g, it comes out to be 2b minus c plus c minus b, right? That's m plus n. So that's 2b minus c plus c minus b, and then comma m plus 2n. So m is 2b minus c plus 2n, so 2 times c minus b. Simplifying, it comes out to be this, and that comes out to be b comma c. So we see that g of this comes out to be b comma c. Thus, given any ordered pair b comma c in the codomain, there is always going to be an x comma y in the domain. Specifically, the ordered pair x comma y defined like this, right? 2b minus c comma c minus b, such that f of x comma y is equal to b comma c. All right, so we've proven that given any pair in the codomain, there is going to be a pair in the domain, namely this pair right here, such that f of that pair is equal to the pair b comma c. So the point is, given any element of the codomain, there is going to be an input that leads to that output, that leads to that element of the codomain. So therefore, G is surjective. Now, by the way, I don't think I gave any questions for homework on this section involving functions like G, where you have pairs of inputs and outputs. I could be wrong, but I don't think I assigned any such questions as homework for this section. So if you didn't fully get this, you'll probably be okay, unless I forgot and I did assign it, but I don't think I did.